So here we're given a question based on relations where they say, suppose that R is called n by R, which is equals to ordered pair of mn, which is an element of a natural number, such that m minus n is even. Then they ask, is R an equivalence relation? So if we're given a question like this, and for us to show that something is an equivalence relation, we need to show that R is reflexive. We need to show that for reflexive, we're going to come and now show that it is symmetric. Then we show that it is transitive. So R is called an equivalence relation if it is reflexive, symmetric, and transitive. So for us to check reflexive, so we're going to first check reflexive. So for us to first check reflexive, it means that if we're going to check reflexive, we're going to first take some ordered pair. The ordered pair we're gonna have let m, so it's gonna be let m be an element of natural num n cross n. We say right now. So we're going to check that. So when we check if n is m an element of a natural cause natural, so we're going to come and apply this definition. The definition says this will be true such that m minus n is even. So in this case, we're going to say such that m minus m is equals to, this will give us 0. We say right. And what is that? That is the same thing as for even. We know this even should be 2 times something. So that is the same as 2 times 0. We say right. Hence, we can say now that we can say hence m is an element of R, meaning that it is reflexive. It's an element of R. And I can say that this is an element of R, therefore, let me say, therefore, R is reflexive. We say right now. So we took mm being an element of n cross n, such that m minus m is equals to 0, and that is the same as 2 times 0. And this is even, it's a multiple of 2. So now we check symmetric. Now when we come to symmetric, we're just going to take the original definition. So we're going to let here mn be an element of n cross n, such that according to the original definition, this says that this minus n is even, meaning that this should be equals to 2k. This should be equals to 2k for some k element of an integer. We say right. And what does this mean? So here I was going to have, this means that if we have here, this will imply that if we have m minus n, what we need to do is commutate this. So we're going to say minus n plus m, right? And then we check. Remember, this is equals to 2k. So I just apply commutative there. Then what we need to check here, is it true that n minus m is equals to 2k? That's what we want to check. If this is also even. You see that? We want to check if this is also even. So we're going to factor out negative for us to check that. We have n minus m, which is equals to 2k. And the negative will be taken by an integer, which will be taken by k. We say right now, for some minus k element of an integer. So minus k will also be an element of an integer. I'm sure we see this. Hence, mn, not mn, nm is also an element of a real num. It's also an element of a rational a relation R. So therefore, R is symmetric. You say right. So R is symmetric. So now since we have reflexive, symmetric, we're going to check transitive. Now for transitive, we need to take 3 elements for transitive. So we're going to take 3 elements. Let's say now we say this. We say that we let, already we have mn, right? So we're going to take them like this. Let's say instead of letting this, I think we can let me check. We can take, let me see this. Yeah, we can have this. We can have, let's say we take this natural number and we take for this one instead of letting. Yeah, I think this is best if we don't let. So for here we can say remember mn being an element of R, which this implies that automatically they say that this is equals to m minus n. This is the original definition, right? M minus n is equals to 2k. And then we say and np element of R implies that n minus p will be equals to 2r, right? For some k are element of an integer. These are integers, k and r. So now the idea is to check if m is related to p. You see, right? So for us to check if m is related to p, what we can do here, we can either add this or subtract them. That is the easiest way I can look at this one. We can add those or subtract. So the best way is to add them. If I take m minus n plus n minus p, which is equal to 2k plus 2r, which this implies that n will cancel n, m minus p is equal to 2k plus r. We say right. And this is the same thing as 2. Can give this w, where w is equal to k plus r, and this is an element of an integer. You see that. Also, this is even, hence I can say that mp is also an element of a relation R. Therefore, we can say that R is transitive. Shall we say this? So since R is transitive, what we're going to say here, we're going to say hence or thus R is an equivalence. R is an equivalence relation. I'm sure we say this. So now that's how the solutions are. We checked if it is reflexive, symmetric, and transitive. Now we come to the second question that we're given. Now the second question says that here now we're given, they say let R be, say let R be a relation from R to R, defined by x related to y if and only if x minus y is divisible by 10. So the word divisible can simply also means multiple of. It can be a multiple of 10 or it can be divisible by 10. So that's what we can have here. So this is how the definition is. Now they say we must show that R is an equivalence relation. They say we must show that R is an equivalence relation. They say show that R is an equivalence relation. Right? Now for us to show this, right, we're going to come here. Remember, for us to show an equivalence relation, we must show that it is reflexive, we must show that it is symmetric, we must show that it is transitive. Right? So for us to show that, we're going to first show reflexive. We're going to first show reflexive. When we take reflexive of this one you see that it's only x related to y. So for this one, we're going to first, now we need to let x be an element of that set where this is defined on set of real numbers. So I'm going to first let x be an element of R. Then now I apply the definition. The definition is that says that for x to be related to y, it should be that x minus y is divisible by 10. So it means that here, since I'm only having a reflexive, it means that x should subtract itself. Then I'm going to get 0. When we check this 0, is it divisible by 10? Or in other words, we should check if this is a multiple of 10. And indeed it is. We say right. So we can say, hence, R is divisible by 10. You see, right? Thus, x is related to x. Now, we know this, and so R is reflexive. So we've checked our reflexive. Now we come to check symmetric. When we check symmetric, I can let two elements. Usually symmetric, we let elements that were given in the initial definition. We're given x and y. So we just have to let these two elements be defined on a set of real numbers, since this is defined on real numbers. And then, according to this, they say that x, you take the original equation or the original definition, which they say that x is related to y if and only if. We say right. They said if and only if x minus y is divisible by 10, meaning it's a multiple of 10. For some, you can say for some k element of integers. You say right. Now, what you're going to do here, we want now to apply commutative to check whether indeed also y is related to x. So we're just going to apply commutative. And this pen, I think it's almost finished, so I need to charge it. $10K. So this will be Let me do this. Let me try to change this screen. So this will be fx out negative y minus x, which is equal to 10k. Then this will be y minus x, which is equal to 10 minus k. For some minus k element of an integer. Right. So the aim here was to check whether y is related to x. In other words, if y is related to x, it means that y minus x should be equal to 10k, and which is true here. We'll say right. So that is correct. So now from here, we can now come and say now, hence r is divisible by 10, thus if x is related to y, then y is related to x. So that is the definition of symmetric. So R is symmetric. We see, right? Then now we come to transitive. When we come to transitive, we're going to say, we're going to take three elements. We're going to let x, y, z be an element of R. And what do we know? We know that x is related to y if and only if x minus y is equal to 10k, and y will be related to z. So in other words, we check if x is related to y and y is related to z. So this in transitive, they are given. Then we're going to verify if x is related to z, if that is the case. So this will occur if and only if y minus z is equal to 10p. For some kp element of an integer, and I can't use the same constant, right, twice, so that's why I'm taking different constants. So since I have this, now for me to check whether this is transitive, I can either, since there's a minus here, I can either add this or subtract them, but I prefer subtracting, right? Or I prefer adding. So we can say x minus y plus y minus z is equal to 10k plus 10p, which this implies that x minus z is equal to 10k plus p, and this is the same thing as 10m, where m is equal to k plus p, which this is an element of an integer. We say, right, hence x is related to z. We agree, right? And then thus r is transitive. So since r is symmetric, reflexive, and transitive, we can now say therefore r is an equivalence relation. We say, right, now we have proven this. So that will be it for now until further questions are asked.